The ability to evaluate solar cell efficiencies under not just the standard spectrum, AM 1.5, but under operating spectra has been greatly expanded thanks to NREL's Spectral on Demand. Hourly spectral radiance data is available from Spectral on Demand at the National Solar Radiation Database's website for all the colored regions on this map. So a good portion of North America, some of South America, and islands in both the Atlantic and the Pacific. Global spectral radiances were obtained using Spectral on Demand for latitude, tilt, and single-axis tracking orientations at the sites marked with blue and green pens. Because multijunction cell structures are included in the analysis, some direct normal spectral radiances are also included in the dataset. These were obtained not from Spectral on Demand, but via the typical meteorological year 3 TMY3 database. All told, this spectral dataset results in about 350,000 spectra that were then applied to the various cell quantum efficiencies to obtain short circuit current densities. Beginning with the ubiquitous NREL best research cell efficiencies chart, we'll be looking at the right-hand side of the chart, so some of the latest best efficiencies for 9 cell types. 4 single junctions were evaluated: silicon, of course, cadmium telluride, SIGs, and single-junction perovskite, and then tandems, perovskite silicon, perovskite SIGs. Finally, the 3,5 multijunctions, 3-junction, 4-junction, and 6-junction 3,5s. In order to obtain operating efficiencies for all of these cells under all of those spectra, the quantum efficiencies shown, as well as the open circuit voltage and fill factor, were drawn from the solar cell efficiency tables. The spectral radiances and quantum efficiencies were converted to 5 nanometer intervals so they could be easily combined. And the quantum efficiencies were normalized so that the resulting short circuit current matches the SDC value given in the tables. The resulting hourly operating efficiencies at 25 degrees C can be summed to obtain annual operating efficiencies, which are compared here against the values under the standard spectrum. For each data cluster, the lateral position of points is organized in terms of increasing site irradiance, running left to right, and the smallest data points at the far right of each data cluster represent the D and I values. Comparing different cell types, we can see divergence in how they perform under operating spectra with respect to the standard spectrum. Silicon and SIGs have outdoor operating efficiencies roughly similar to what we see under the standard spectrum, whereas cadmium telluride and single junction perovskite tend to have higher operating efficiencies under operating spectra, and all the cells with 2 or more junctions tend to have lower efficiencies as a result of the operating spectrum conditions. If we plot the data relative to the efficiency under the standard spectrum, we again see the spread in performance that results from operating spectrum variation. And even for silicon, which looks more tightly clustered around its standard spectrum value, the efficiency spread here in relative terms is about 5%, which is equivalent to 20 degrees C of temperature excursion. So this begs the question as to whether we should be characterizing efficiency using more than just the single spectrum. Despite the availability of standard methods for characterizing energy yield, it's the efficiency under AM 1.5 that is most often seen on data sheets, in reports, and even in warranty coverage terms. Relative to SDC, we already have different temperature and irradiance for operating conditions, so maybe it's time to think about having a standard operating spectrum as well. The usefulness of having more than one standard condition is familiar outside the solar realm. Here we have the EPA's vehicle fuel economy ratings for 2021 passenger vehicles, and the city mileage rating plotted against highway miles per gallon. 2021 vehicles that run purely on gas I've labeled as gas guzzlers because I'd say in 2021, with all of the electric vehicle options out there and the roaring threat of climate change, any new car that runs purely on gas is truly a gas guzzler now. Comparing the gas cars in gray to the EVs in green, we see that the gas cars do better under highway conditions than in city, And conversely, the EVs do better in city conditions than on the highway. So testing under either single condition would be misleading. And in fact, we get cases like those shown on the right, where if we used only the highway rating, we would find cars that look identical under highway test conditions perform very differently under city conditions. And therefore, there's the need for the two measurement conditions. Reporting cellular module efficiency under two different spectrum conditions does not require testing under two different conditions, because the results from one can be translated to the other via spectral mismatch correction, as long as the quantum efficiency of the cellular module is known. So while the desirability of having a standard operating spectrum has been known for some time, the main impediment to obtaining one has been deciding what that spectrum should be. But as with the city and highway mileage example, the specifics probably matter less than simply having two conditions. Few people know or remember what the test conditions for city and highway are, or even realize that they changed recently. The value to the vehicle buyer is having two conditions which allow a bracketing of the operating conditions for the vehicle. To obtain something similar for cells and modules, three candidates are shown here. In orange is a composite of all the spectra used in this study, and on the right is shown the efficiencies that result. But a more practical choice might be one of the existing standards that is already qualified. So that would be either AM 1.5D or AM 0, the standard for space. There are pros and cons of each, but for comparing different cell types or for making predictions about energy yield in the field, two spectra is going to be better than one. I hope this work stimulates some interesting discussion, and further detail and analysis can be found in an upcoming issue of Solar Energy.